What if I told you that most of the buildings where you live, work, or study are hiding a secret? A technology that didn't even exist a century ago, yet now is everywhere. Virtually every iconic building, from London's Shard to Dubai's Burj Khalifa to New York's One World Trade Center, relies on this hidden innovation. Imagine any modern cityscape. It's always right there in plain sight, yet invisible to most. Like the air we breathe, we heavily depend on it, but rarely notice it exists. This secret is the curtain wall. And thanks to recent advancements in unitized facades, today's curtain walls are almost unrecognizable from their original form, cleverly disguised to look like anything but the curtain wall. But how exactly did curtain walls evolve from simple glass screens into sophisticated high-tech envelopes dominating architecture today? This is a story of architecture's most influential innovation. By the end, you will understand exactly why curtain walls have become the backbone of modern buildings design. To understand today's curtain walls, we need to go back to the beginnings of the last century. The term curtain wall originally described any non-load-bearing facade, whether masonry, glass, or precast concrete. The idea was beautifully simple. If the facade does not bear structural loads, it hangs from the building's structure like a curtain. But then Walter Gropius designed the Facade factory in 1911, introducing the first continuous glass corner in the architectural history. This minimalist grid of vertical mullions and horizontal transoms became the DNA of modernism, industrial, alien, and utterly contemporary. This grid system, where apertures between mullions and transoms are filled with glass or opaque panels, became the most ubiquitous urban fabric element. Today, it doesn't matter if it's school, office, hospital, or apartment building, curtain wall can be used anywhere. It became the ultimate architectural mask. The first true curtain walls were what we now call stick systems, and their fundamental principle hasn't changed in over a century. Vertical profiles, mullions, attach to the building slabs with brackets. Horizontal profiles, transoms, span between mullions, and glass or opaque panels fill the created apertures. Here's the crucial engineering insight. The glass carries no structural load. It simply rests on horizontal transoms and is laterally secured around the perimeter of the aperture. The mullions and transoms transfer all loads back to the building structure. But here is critical detail that makes tall buildings possible. Movement accommodation. Stick curtain wall mullions are split at every floor or every other floor and connected with spigots. These connections allow the facade to move up and down, accommodating both deflection of the building slabs and thermal expansions of materials. Early curtain walls were designed as what facade engineers call perfect barrier facades, completely sealed envelopes preventing any air or water penetration. At least this is the plan. The glass and metal panes themselves were waterproof, but the joints were the weak link. Since facades hang from structure and move with building's movement, early putty seals couldn't accommodate this motion. Putty is rigid. Buildings move, putty cracks, and you get expensive, leaky facades that nearly kill the curtain wall concept altogether. The breakthrough came from an unexpected source: the automotive and aerospace industries. Silicons and rubber gaskets, originally developed for airplanes and cars, found their first adoption in buildings in refrigerator doors, and only in the middle of the 20th century were adapted for curtain wall and window seals. These elastic materials could accommodate movement while maintaining waterproof barriers. Just gaskets on their own could not solve the leaky joints. Early curtain walls were made of steel sections. These steel sections were very simple geometry, and they warped during the manufacturing process. Steel also corroded when exposed to water. All that created gaps. Worse still, metals are very thermally conductive and created horrific thermal bridges. The next breakthrough was aluminium, but not for the obvious reasons. Aluminium is even more thermally conductive than steel, and yes, steel corrodes while aluminium does not, and yes, extruded aluminium profiles aren't as warped as steel sections, but the real revolution was the precision. Second World War resulted in significant advancements in aluminium manufacturing. Aluminium now can be extruded into very precisely shaped profiles with intricate details specifically designed to accommodate polyamide or plastic thermal breaks, and crucially, the gaskets required for air and weather sealing. Even though aluminium is more thermally conductive than steel, the precision manufacturing capability more than compensated for this drawback. Thermal breaks, small barriers of insulating materials inserted into aluminium profiles, prevent heat transfer. But the thermal problem wasn't solved by thermal breaks alone. The real game changer was structural silicons and glazing units. Glazing units aren't just multiple glass panes, they are engineered assemblies where glass panes are bonded together through spacers with gaps filled with the inert gases like argon. This dramatically improved U values, making curtain wall thermally efficient for the first time. What was once cutting-edge, double-glazed units with 2 glass layers, is now considered subpar thermal performance. Today's building standards require triple-glazed units featuring 3 glass panes separated by 2 engineered cavities, each optimized for specific thermal requirements. Here's a detail most people never notice, but which makes modern curtain wall possible: the chamber between seals. Every glazing unit has an inner gasket between the profile and glass, and an outer gasket between pressure plate and glass. The space between these gaskets creates a pressure-equalized chamber that is drained through weep holes in the outer seal. This isn't just about keeping the water out, it's about managing the inevitable water that gets in. By controlling pressure differentials and providing drainage paths, this system ensures that even when the outer seal is compromised, water doesn't penetrate into the building. This principle, accepting that some water will penetrate and managing it rather than trying to create perfect barriers, was revolutionary in facade engineering. So here's how modern curtain wall facades deal with air, water and thermal insulation. There are mullions and transoms holding the glass. The glass is retained to the profile with toggles, structural silicon or pressure plates as shown here. There is a thermal break between the pressure plate and the profiles. The first outer seal prevents most of the water from entering, and the second seal prevents air and water from getting inside the building. The chamber between the seals is drained through the weep holes at the outer gasket or silicon joint. As buildings got taller, stick systems hit practical limits. Imagine assembling a curtain wall piece by piece, 100 meters in the air, in all weather conditions. This system requires external access in the form of scaffold or mast climbers. For a 50-story tower, you spend at least 1 week to erect scaffolding per floor and another week to strike it. That's potentially 2 years just providing access to install facade. Enter unitized curtain walls. Entire facade sections or units built in controlled factory environments, delivered to site and craned into position without the need of access externally. That saves months and years of construction program on tall buildings. But there is a fundamental difference. Stick systems have continuous mullions, while unitized systems break that continuity. Each unit must connect to neighbors through sophisticated gasket systems and precise brackets. And the joint between the units is designed with similar two-stage seal philosophy, with the outer gasket allowing some of the water in and the inner gasket providing ultimate air and water barrier. These additional gaskets and highly engineered brackets are expensive. However, the payoff is enormous. You can install 1 story per week with no external access required. For that same 50-story tower, you've gone from years of scaffolding to direct crane installation. In unitized systems, the joints and gaskets between units do all the movement accommodation work. The facade still moves with the building, but now the movement is managed at the unit interfaces rather than within the continuous mullions. As technology advanced, architects began asking, why do we need visible mullions at all? Spider curtain wall systems answer this question with engineering poetry. Instead of traditional grids, spider systems use point-fixed glazing. Glass panes are held by small mechanical connections at discrete points. These brackets look like spiders, hence the name. These curtain wall screens typically connect to the tension cables behind the facade. This creates continuous glass surfaces. The structure nearly disappears. These facades are commonly suspended from the top rather than supported at the bottom. This allows the steel sections carrying dead loads to be extremely thin. The visual impact is dramatic. To handle wind loads, the cables are kept in constant tension. This tension transfers extreme forces to the building structure. The glass panes are point-fixed. This makes stress within the glass much more demanding. The engineering challenge is significant. Both glass and building frame must do far more structural work. This requires entirely new glass types and connection methods. The technical complexity is enormous. But there is a reality check coming. These facades are extremely expensive. They are almost always unique designs. They offer no additional thermal, energy or acoustic benefits. Their only advantage is aesthetics. We are seeing fewer of these systems as the industry matures. Performance and efficiency now drive design decisions. But it is important to understand what made these facades possible. Floor-to-ceiling glass and point-fixed glazing in curtain walls demanded new safety standards. The stakes were suddenly much higher. Heat-treated glass emerged as the first solution. Tempered or toughened glass is heated to extreme temperatures and rapidly cooled. This provides 4 times the strength of a regular annealed glass. When it breaks, it shatters into small pieces. These are far less dangerous than large shards of annealed glass. But for all glass facades, even small pieces weren't good enough. When glass serves as a barrier protecting people inside, it must do more than just be strong. It must stay in place and continue serving as a barrier even when broken. This became possible with laminated glass. Multiple glass layers are bonded together with transparent film. The industry calls this an interlayer. When laminated glass breaks, pieces remain stuck to the plastic film. The barrier stays intact until replacement. These advances made all glass facades not just possible, but practical. They transformed glass from fragile material into a reliable structural component. Think about this for a moment. Floor-to-ceiling glass skyscrapers would have seemed just like pure fantasy just 70 years ago. Today, they are so common we barely notice them. Glass became so strong and reliable that it could serve as a primary structural component in some buildings. The impossible became routine. But there were still few considerations to solve. Like thick masonry or concrete facades, curtain walls are lightweight. They lack the mass that makes traditional walls good sound barriers. The solution came through already familiar technologies: insulated glazing units and laminated glass. The principle is simple: more glass panes mean more mass. Thicker glass means better sound insulation. Separation of panes with spacer and gas chambers adds to acoustic performance. Surprisingly, the film interlayer in laminated glass helps enormously. It acts as a sound dampener between glass layers. Here's where it gets clever. Combining different glass thicknesses and spacer widths within one glazing unit makes it asymmetrical. This reduces reverberation. Acoustic insulation improves even further. As a byproduct of thermal and safety improvements, facade engineers solved the acoustic problem too. But curtain wall grids created a new acoustic problem: flanking sound transmission. Traditional masonry facades did not have this issue. Noise travels through the facade structure itself. Hollow mullion tubes can transfer sound from floor to floor. Transom spanning between neighboring apartments do the same thing. In steep curtain walls, mullions could be split between floors to break the sound paths, and hollow profiles can be filled with acoustic inserts. Unitized facades had a built-in advantage. Profiles are already split and separated by gaskets. This creates natural sound breaks between units. With acoustics and thermal insulation problems solved, we finally cracked the code. All glass curtain wall facades were unlocked. Light could flood inside buildings. But this created a problem in itself: overheating. The first all-glass structures weren't built in the 20th century. They were much older. But they weren't homes, factories, or offices. They were greenhouses. They allowed all solar light in and kept the heat trapped inside. In greenhouses, it is a feature. Modern all-glass facades created the same greenhouse effect. Buildings became solar ovens. In glass buildings, it is a bug. However, this problem was promptly solved in the second half of the 20th century. The solution was air conditioning. But these buildings became prohibitively expensive to run. Having high-performance glass coating helped somewhat, but the only way to truly minimize overheating is solar shading outside the facade. External solar shading, called brise-soleil, works effectively, but it requires regular maintenance. It also compromises the pure all-glass aesthetic that architects wanted. There is not a problem. Solar shading gets in the way of maintenance personnel. Try cleaning glass when you are suspended from a rope, now add horizontal shading element blocking your path. The solution was double-leaf curtain wall facades, essentially curtain walls within curtain walls. Solar shading sits protected in the cavity between them. It is an elegant engineering solution, but it is very expensive. You are effectively building two facades instead of one. Most importantly, these facades work for offices but are hardly suitable for residential applications. People want to open windows in their apartments, they want balconies, they want connection to the outdoors. Double-leaf facades can't offer that. The inner leaf is typically sealed, no operable windows, no direct access to fresh air. That and the extreme cost of these facades made them a rare breed. But one of the main problems with all-glass facades is fire safety. It's now possible to create all-glass facades without any opaque areas, not even in the spandrel zone between floors. The so-called single transom or zero spandrel detail is highly desirable to architects. This creates the minimal look of pure all-glass facades. Stopping flanking sound transmission is manageable, split the profile or fill them with acoustic inserts, but stopping fire propagation is a different challenge entirely. With zero spandrel all-glass facades, fire destroys the glass in minutes. The fire then leapfrogs from one floor to another. In most countries, these all-glass facades are effectively banned. Building code mandates minimum spandrel zone dimension between floors. The aesthetic dream crashes into safety reality. However, some countries still allow these details, but these buildings require active fire protection. Sprinkler systems minimize risk of fire propagation between compartments. That adds significant costs. All glass facades are expensive. They are not thermally efficient. They require extensive engineering to mitigate created risks. The cost-benefit equation doesn't add up. And quite frankly, they are going out of fashion. They became so ubiquitous that glass buildings are no longer a miracle. They are rather boring. The novelty has worn off. To address costs and changing architectural fashion, curtain walls evolved even further in recent decades, particularly unitized curtain walls. They changed beyond recognition, so much so they are now commonly called unitized facades. Today's unitized facades can masquerade as anything. Modern unitized systems deliver all prefabrication benefits while appearing as rainscreen cladding, traditional masonry, precast concrete, or any architectural vision. They are the same frames made of mullions and transoms with gaskets between them. They are attached to the buildings with intricate, highly engineered brackets. Openable windows are placed within these frames. Even balustrades attached to them. But all that structure is hidden by decorative elements. The glass area decreases to about 40% of the overall facade. The rest is filled with insulated aluminium panels and covered by rainscreen cladding. The options are endless. Decorative metal, brick slips, stone cladding, terracotta tiles, or glass-reinforced concrete panels. Any combination of thereof. The possibilities are limitless. This is curtain wall evolution's ultimate achievement. High-performance prefabricated envelopes adaptable to any architectural style. Most of the time you can't even tell it's a curtain wall facade. The structure disappears completely behind the architectural expression. The engineering becomes invisible and the performance remains exceptional. This mastery of global supply chains and prefabrication unlocked curtain walls key to widespread adoption. They can be manufactured anywhere, shipped globally, assembled with relatively modest skill requirements. Modern curtain walls aren't perfect. They are approaching fundamental thermal limits. Insulation can only be added to the opaque areas between profiles. Adding it behind the vapor control layer risks moving the dew point temperature inside the building. This creates interstitial condensation problems. If we are serious about highly thermally efficient facades, we may have reached curtain wall limitations and we have to innovate even further. New breeds of unitized facades are emerging. Some use glue-laminated timber as structural profiles instead of aluminium box sections. Wood offers better thermal performance and smaller carbon footprint than metal. But it has its own issues with moisture control and fire safety. And whether these facades breeds will survive this step of evolution remains to be seen. Innovation doesn't guarantee adoption. Performance, cost, and constructability still rule. Retrofitting existing facades represents our biggest future challenge. Curtain wall facades built in the 20th century are approaching their end of life. They need retrofitting to match new energy standards. Here's the problem. It's impossible to fit triple glazed units in frames designed for single panes of glass. The dimensions simply don't work. The structural capacity isn't there. This is driving innovation in areas like vacuum glazing. These units can fit existing frames while dramatically improving thermal performance. They're engineered specifically for retrofit applications. We are no longer focused on building outlandish new designs. We are becoming more future-orientated, gradually improving existing systems while addressing millions of square meters of older facades needing upgrades. New facades are now designed with future retrofits in mind. Parts will be repurposed or recycled. Sustainability drives design decisions. Curtain walls have become the backbone of globalized construction. They address labor shortages, quality control issues, and increasingly complex performance requirements. They can be fabricated anywhere and assembled with relatively low-skilled labor. But unlike iPhones, you cannot replace building facades every year. Innovation cycles are long. The consequences of mistakes are measured in decades. This is why facade engineering moves cautiously. Every innovation must prove itself over time. The next time you walk through a city, look up at those facades around you. You are seeing nearly a century of engineering innovation. Each building represents thousands of small breakthroughs that collectively transform how we build and live. All facade types have their place in this ecosystem. The curtain wall revolution isn't over. It's evolving to meet new challenges of energy efficiency, climate resilience, and global construction demands. From Walter Gropius's first glass corner to today's sophisticated unitized systems, curtain walls continue reshaping our built environment in ways both visible and invisible. If you like this video, please subscribe to our channel. Make sure to check other videos on facade engineering and other facade types. from concrete to rainscreen to insulated render systems. If you would like to go deeper into any of these topics or become a facade engineer, check the courses and qualifications we offer at the Institute of Architectural Science and Technology. We offer many free courses, so make sure to explore them. As always, all 3D models and drawings from this video can be found on the Facade Intelligence platform. Make sure to subscribe to the free plan. Thank you for watching, and we will see you in the next video.